Hi everyone, welcome to the ninth episode of the Math and Beyond and this podcast. Today we are going to talk with Thomas Bax. He is a PhD student from the University of Utrecht, and he is doing his PhD in cosmology. He studied mathematical and theoretical physics as a bachelor degree, and as well as a master degree, both at the University of Utrecht. So I will now send him the invite, and I will see you in a second. Hi, Thomas. I'm disconnecting to the audio. Meanwhile, I wanted to introduce the topic of today, which is the Poincaré Conjecture and the application to cosmology. Speak, Thomas. I think I can hear you.
Yeah. Sorry, I couldn't hear you for a second, but yeah, it's all good. I don't think I missed much, right?
No, don't worry.
Good.
Yeah, I gave a small introduction about you. I said you pursued a bachelor and master degree studies in theoretical physics and mathematics at the University of Utrecht, and you are now doing your PhD in cosmology, still at the University of Utrecht.
Yes.
And that's it. I then introduced the topic of today, which is the Poincaré Conjecture and the application to cosmology. So I would say, first of all, I wanted to ask you, how are you?
Yeah, I'm good. Yeah, just had dinner. Long day at work, so it's pretty routine.
Okay.
Yeah.
So today also was not. I don't know how it was in Utrecht, but at least here in Amsterdam, it was like literally raining all day long.
Yeah, for sure. It was the same.
So yeah, not the very best day in May, hopefully, but we will see.
Sure, but good day for podcasts, right?
That's right. That's right, actually. So yeah, I think we can jump into it. I will ask you very straightly, what is the Poincaré conjecture, and why is it important? Why is it relevant? We know that a conjecture is an open problem which is not solved. We know that the Poincaré conjecture has been solved by a Russian mathematician, Grigori Perelman. But why should we care about the Poincaré conjecture? What does it relate to? What is the problem?
Right. So I guess that question might have different answers depending on what you consider. What is your field of expertise? Are you a mathematician? Are you a physicist, cosmologist? But I mean, originally this was just purely a question of mathematical interest, right? So this was one of the Millennium Prize problems. I don't know if you're familiar with this list. Been compiled at the turn of the century, basically. So in the year 2000, somebody, or I think a committee of mathematicians compiled a list of problems, which
1900.
Sorry?
Yeah, you said 2000. I think you meant 1900.
Sure. I think I do.
Oh, sorry.
No, these are not the Hilbert problems, right? This is.
Yes, you're right.
Yeah,
because
I think. I was confused for a second too, but yeah, I think it's the year 2000. Yeah, so there we go. Really, millennium, right? Not.
Yes.
Yeah. Right. So at the turn of the 21st century, this list was compiled. Well, these are basically some of the most influential problems in mathematics that exist today, and a lot of them are. Well, I shouldn't say a lot. Some of them are very, very difficult to even understand what the statement is about. They're very, very abstract, but nevertheless, they have extremely far-reaching consequences if they were to be solved. Some of them are a little bit more tangible, like P versus NP, for example. And also, in intuitive language, I think the Poincaré conjecture is relatively easy to understand, but still requires a little bit of a little bit of introduction. So the idea is that mathematics is about structures, right? And what mathematicians like to do is they like to classify things. So once they've come up with a certain object, like let's say a manifold or a group or a set, they would like to be able to define some kind of notion of equivalence between these objects and then say, okay, how many of these objects can I find up to this equivalence? So just to give you a very simple example, right? Let's say I'm studying finite sets. So a finite set is just a collection of elements, right? It's just, could be the numbers 1 to 10, or it could be you and me, right? That's also a set with 2 elements. And then I might say, well, okay, when are 2 sets really kind of the same thing? Because a set is just, it's a collection of elements. So then I might say, well, really a set is just the same as some other set when there is a bijective mapping between them. Is that something that you would be familiar with?
Yep.
Yeah, sure, right. So then I can say, okay, I have some notion, I have some object like a set, finite set, and I have some notion of equivalence between them, which is when there exists a bijection between them. And then I can say, okay, how can I classify all finite sets? And the answer is pretty simple. You just need to say how many elements they have. So this is in some sense like an enumeration of all different types of finite sets that you might have up to this equivalence. And you can consider other examples as well, which would require more introduction. Like you can classify, I don't know, finite groups up to isomorphism, or you can classify manifolds up to diffeomorphism, etc., etc. For many, many different mathematical objects, there is like a notion of equivalence. And then a very natural question is, okay, how many classes under this equivalence do you have? And what this Poincaré conjecture is about is it's not exactly that, but it's kind of related to so how many 3-dimensional manifolds do you have which satisfy a certain number of properties up to homeomorphism. So it's really a topological problem. So
okay, well, can you explain 1 second very briefly, the sentence up to homeomorphism?
Yeah.
Okay, so firstly just literally in 1 sentence try to describe what a manifold is, and then what do you mean with up to homeomorphism?
Right. So here the notion of equivalence that I'm referring to is, so the object that I have is a topological space, and a topological space just means that you have a set, but now it's not just a set, it has a little bit more structure, namely there is also some kind of notion of nearness between points. It's not quite like distance, it's a little bit more fuzzy than that, but you can imagine that
is it a metric, or
sorry?
Is it a metric or a topology?
No. Not really. It's a little bit more low level than that, but you can imagine like in topology, things are the same, like 2 objects are the same. If you can sort of take them as a piece of clay and then deform one into the other. So, for example, like the sort of the famous example that people always use is like a coffee mug is the same as a donut, right? I don't know if have you heard of this before? Otherwise, you'd have to visualize it now. But
no, I do.
Yeah, right. So the idea is if I have some coffee mug with an ear attached to it, then that's really the same as a donut, because I can just sort of like I can squish the mug part, and then I just have something with a hole in it, and then I can stretch it out a bit and make it circular again, and then it's a donut. So that means that in topology, a coffee mug is the same as a donut. And that is what homeomorphism means. So it just means that you have two topological sets, without me really saying what topology is, but that would be a little bit contrived. So you have a topological space, the coffee mug, and you have a topological space, the donut. And there exists a homeomorphism between them, precisely because you can sort of mold one into the other and vice versa.
I think it's worth. I think it was worth to mention. Because maybe one can say, but if I have, I don't know, this, I think, the lipstick.
Sure.
If I have a lipstick, I can also make a hole in it, and then it is the same thing as a donut. But homeomorphism, right, implies that transformation should not undertake gluing or tearing.
No, exactly. So also, right, you cannot cut or paste. You can only mold. So, for example, like a line segment is not the same as a circle, because in order to deform one into the other, you would have to cut the circle, or you would have to join the endpoints of the line segment, but that's not allowed. So then the question in the Poincaré conjecture is like, okay, if I have a three-dimensional space, a three-dimensional manifold to be precise, where this manifold has, in some sense, it has two properties. Namely, it has finite volume, right? So think of a three-dimensional manifold as just some, blob of stuff that you can visualize in R3, kind of like a cloud, sort of. And then the question is, okay, if I have such a blob, and that blob has the property that whatever circle I draw in that blob, I can sort of smoothly contract it to a point within that space. If the space has that property, then the space must be homeomorphic to a three-sphere. To a three-ball. So it means that if I have this blob, then I can sort of I can deform it very nicely and smoothly until it's just a ball, basically. And it sounds very intuitive, right? I can, whatever, how many weird, appendages or tentacles this thing has, I can sort of like pull them all in, and I can mold it a little bit, and then it's a ball. Okay. So it sounds intuitive. And but one thing, for example, that when you think about it a little bit more, this condition that I mentioned about this loop, you do need that, because, for example, if you imagine you have like a solid donut, that's also a three-dimensional space with finite volume. But this donut, I cannot make it into a ball without breaking the donut, right? And the reason why it doesn't work is because in this donut there is a circle, right? There is a loop, namely the one that sort of goes, horizontally around the equator, and that loop, I cannot shrink it to a point, right? Because there's a hole in this donut, so to speak. So this condition about these loops is just to prevent the manifold that I have from having holes, basically.
Okay. And how? Yeah. Does it have? Because you say, yeah, it is fairly intuitive, but does it have? Why is it important?
Well, it's important because, well, okay. So here I should say, it is important in the first place to mathematicians because manifolds are objects, so three-dimensional spaces. I haven't really said what a manifold is, but just think of it as three-dimensional space. A three-dimensional space is a very, it's a very simple, sort of a very elementary mathematical object. So, if you think of objects that you might try to classify, these three-dimensional spaces are sort of like, it could be possible to classify them, right? They're not so complex and super weird that you can never hope to classify them, but it's also kind of a challenging problem, right? In an ideal world, mathematicians would like to classify everything, but in practice they almost never can. But this is like an example where three-dimensional manifolds are objects that are very difficult to understand, but still they can be understood. So it's sort of it's a natural place for such a problem to appear. For example, classifying one-dimensional or two-dimensional spaces turns out to be relatively easy. There are, let's say, if you do a master's in abstract mathematics, then you probably know most of the details of how to classify one- and two-dimensional spaces. But three-dimensional spaces is very, very hard. So it was sort of the next thing on the list, if you like.
Okay. And let's say, how does, you mentioned before topological spaces. So we know that in this conjecture, when talking about this conjecture, we are within the field of topology. Can you, briefly, let's say, in 2 sentences, give the definition, let's say, of topology and how it relates to the Poincaré conjecture? Why are we in the field of topology when we are dealing with this conjecture?
Yeah, well, okay, how let me think. So topology is okay. Let me first try to explain in a little bit more detail what topology is. So imagine that right, sort of the simplest mathematical object that you could consider, like the lowest level thing, is just like a set. And a set does not have a lot of structure, really just has a number of elements, basically. But these elements, they're not really interrelated in any way. There's no there is no notion of distance between them. There's no ordering. There's no there's really nothing besides just, you know, elements being labeled by some index, if you like. Now, then you might say, well, but actual sets that we encounter in everyday life, they have more structure than that, because, for example, there are sets that I can draw on a picture. There are sets that I can draw in a plane, or in three-dimensional space, or, you know, donuts, circles, lines, planes, these kinds of things. So to describe that, you would like to have something a little bit richer, so to speak, than just a set. And you might say, well, I could consider things like sets where for every 2 points, and this would be very intuitive, right? But in some sense, topology is a little bit less intuitive. But what you could say is like, okay, I have 2 points in my set, and then for every 2 points, I can define a distance measure between them. And then you would have what is called a metric space. And for metric spaces, you would say that two things. So now you have an extra map, if you like, which is this distance map that takes 2 points and calculates the distance between the two.
Yeah.
Okay. And then you might say, okay, what would then be a notion of equivalence between two metric spaces? So a notion of equivalence between two metric spaces would be like, okay, I have a map from one set to the other set, so that for every pair of points that I have, the points that they get mapped to, they have the same distance between one another. So sort of distance is preserved, if you like. But then that would be, so for example, in that case, let's say that you had a line segment from 0 to 1 and a line segment from 0 to 2, then these spaces as metric spaces, they would not be the same, because you cannot map this line segment from 0 to 1 onto a line segment from 0 to 2, just because the line segment from 0 to 1 doesn't have any points that have distance more than 1 between them. So somehow that doesn't really work. So with what you've just defined, these two spaces would not be the same if you consider them as metric spaces. But what you would like to do is, or well, what mathematicians like to do is they like to say, okay, I would like to have some notion of equivalence that describes precisely this intuitive notion that I should be able to, kind of pull things apart or squish them together, so as that when I can do that, they are still the same. So it's like a little bit more flexible, literally, and that is, in some sense, that is exactly what topology does. But I really don't think that it would be I really don't think that if I give you a definition of what a topology is, it might sound like I'm kind of beating around the bush, right? But if I give you a topology, like if I give you a definition of what a topology is, it would not be very illuminating. It's
Okay.
it's a very it looks very contrived, but it does exactly what you want it to do. So it's like it's a set, and then instead of having distances between points, you have some collection of sets that satisfy certain properties, all of which are subsets of your space. And then that collection of subsets, together with the whole set itself, that is what defines a topology. And then you can define some notion of equivalence between topologies, which preserves this set structure, whatever it is. And then it turns out that when you go and actually when you put this in practice and you say, okay, let's try to now decide whether with this new notion is 0 to 1, is it the same as 0 to 2, and is a circle the same as a line segment or not, etc., etc. It turns out that it does exactly what you want it to do. So I think that's probably the best way to look at topology, that you have some kind of intuitive notion that you would like to make precise, and topology is that instrument. That's how I would explain it.
Okay.
Right, because we're just humans, right? We have kind of an intuitive knack for what's going on, and we're trying to formalize that. That's, well, at a very basic level, that's what mathematics is about. And then you just try to define it. You just try to write something down, and you play around with it a little bit. You see if it does what you want it to do, and if it does what you want it to do, then you are happy.
Okay, mathematics in a nutshell. Okay.
Yeah, now, it really is. Yeah.
To go forward with our talk, and we would like to. I want to expand more onto the cosmology side, relating to the conjecture. And to do that, I need to ask you before a question that might seem unrelated at the moment, but it is: do we find any inconsistencies? Do we have any problem with our current most adopted cosmological model, the ΛCDM model? Are there any observational data that we cannot explain? Because we have this cosmological model, but one may say, yes, okay, we are done, nothing to do anymore. Well, there are. It would be nice. However, it does not explain everything. No, what do we not explain, and what are its limitations? What problem do we have with it?
Okay, so I have a pretty long answer to that, I think, but it's pretty important for the rest of the talk. But let me just begin by saying that you had a previous guest on this podcast where you basically discussed the underpinnings of ΛCDM, right, as a cosmological model. And ΛCDM, like at its most basic core, is like you have, and I will explain this statement. It's like you have general relativity, that's one thing, and then you have symmetries, that's the other thing. And when you make them kiss, that's when you get ΛCDM in some sense.
Okay, what do you mean? What do you mean by that?
Right. So when Einstein first figured out, or conjectured, if you like, that general relativity was the theory of gravitation that would correctly describe things beyond the Newtonian regime, so where masses get very heavy, and when distances,
when gravity is the main force. Yeah.
Sorry?
Yeah, when I say gravity is the overcoming force of all the others.
Right. So then what happened was, well, okay, so we have these Einstein's equations, right, which say that, okay, you have the metric, which is about curvature of space-time, and then you have this energy momentum tensor, which is about the matter content of the space-time, and they have to be related in some way. So Einstein's equations basically tell you, okay, for given matter content of the universe, how should the universe curve itself in order to accommodate all of that matter content, or the other way around. If I have a given metric, a given geometry in the universe, how is matter going to move in that geometry, right? If you think about the motion of planets or whatever stuff about black holes, it's so that this is kind of two ways of saying the same thing, right? They should be interrelated, the matter and the geometry.
I like to use to explain say general relativity in a nutshell. I like to use the popular sentence, which, to be honest, made me sort of grasp it very superficially in first place, saying that goes like this: matter tells space how to bend, and space tells matter how to move. That's I think it I would say it involves the relation that you were talking about.
Yeah, exactly. I mean, I said exactly that, but with more words, right? It's exactly that. It's true. Then you have this you have general relativity, and okay, the you have some idea of what this stress tensor, right? What this matter content of the universe could possibly be, right? There could be things like ordinary matter, so to speak. There could be some radiation. There could be maybe some other particles that that make up the matter content of the universe. But one immediate problem that comes up, and which I think is, I think, you know, anybody who does cosmology probably knows this, but it's good to be aware of it. But like, if you just forget about general relativity for a second, but you think about special relativity, then if we are an observer, then if there is light coming at us from a certain place, then all the events that we can observe, they are in our past light cone, right? So because the speed of light is finite, you can look back in time, but you cannot look back everywhere in time, so to speak, right? There is some region of space-time that you can simply never access, because these things are so far away from you that even light could not travel the required distance within the required time, so to speak. But if, and this is what you're trying to do in cosmology, if you're trying to say, okay, I want to now say something about how the universe evolves as a whole, right? So I want to picture the universe in like right, the way you draw these space-time diagrams, so as time goes up, right? And then the universe is just sort of evolving in this direction. So you have like a spatial slice at some fixed moment in time, and once and then as time progresses, this space-time slice with all the matter on it and all the planets and all the stars, etc., sort of evolves in this direction, right? But in order to take Einstein's equations and actually compute how this evolution works, you need to specify, just like with any differential equation, if you like, you have to specify initial conditions. You have to specify boundary conditions, if you like. And
what do you mean by boundary condition?
Just like when you solve a differential equation, you have to say what is the, let's say you have a second order differential equation. Then in order to provide a unique solution, what you have to do is you have to say, okay, what is at time t equals 0, what is the value of the function, and what is the value of its derivative, right? If I don't do that, then I don't know what the solution is. There's going to be infinitely many of them generically.
Okay.
So that's what I mean by boundary conditions. And for the universe, it kind of works in a similar way, except that this differential equation is hugely complicated because it's Einstein's equation. It's completely nonlinear. It's very, very difficult to understand. But still, it's a differential equation that when you want to solve it, you have to specify initial conditions. So what we hope to do is to, take a bunch of observations and say, okay, these are our observations, and now these are basically, our observed initial conditions. And then with these initial conditions, we can take the Einstein's equation, we can plug it in, and we can solve for the evolution of the universe. So that's what, in an ideal world, that's what we would hope to do. But it turns out that this is impossible, simply because if you want to specify, the boundary conditions that you need in order to determine the evolution of the entire universe, then you need to specify these boundary conditions on like an entire slice. Because if you only specify what happens at some fixed region of that slice, then only everything in the future light cone of that slice will be determined by that. But in order to really, compute the evolution of the entire space-time, you need to specify initial conditions on an entire, basically on the entire universe at some fixed point in time. And only then can you do this evolution.
Yeah.
But if we can look back in time and we can only observe, not this entire slice, but rather only things on our past light cone, then how are we going to do this, right? I imagine I draw this diagram and I observe some data on my light cone at some point in time. So on my past light cone at, I don't know, t is 5 billion years ago. And then I can observe some things, but I can never observe the entire universe at that moment in time, simply because the speed of light is finite. Which means that in order to go from what data I actually have from my past light cone to now say something about what is going on with the entire universe at t is 5 billion years ago, I need something else. And that something else I cannot find within, only general relativity. I really need to add something on top of that. Does that make sense? And so that thing that I need to add on top in order to, make my evolution problem well defined that thing that you need to add is symmetries. And symmetries basically say, well, okay, and that is also what this what these conventional ΛCDM models are all about. Is you say, well, let's say that you look back in time and you see, for example, the temperature of the cosmic microwave background, and you see that well, it's whatever it is, 2.7 Kelvin, right? Then you have observed that only on your little past light cone, but then you say, well, and this is a this is a purely, well, this is like an aesthetic argument, right? You say, okay, it's 2.7 Kelvin, but our place in the universe is nothing special. In some sense, this really goes all the way back to Copernicus, when people figured out that, the position of the Earth was really not the center of the solar system. We are just some rock orbiting the sun, and we are not the center of things. There's nothing special about our position in the universe, and this is sort of an extrapolation of that, sort of an ultra Copernican principle, if you like, and it's called roughly speaking, this is what the cosmological principle entails, and it says basically that the universe looks the same pretty much everywhere. And it's intuitive, right? Why would it not be? Why would the universe be, well, that's basically what it's saying, is why would the universe be weird? Why would we be at a special position? There doesn't seem to be any reason why that should be the case. So we're just going to assume that it's not the case. And if we do that, then we can say, well, from our perspective on our little past light cone, we see that the temperature of the CMB was 2.7 Kelvin. And therefore, we know that on this entire slice, at whatever redshift the CMB is, we know that the temperature, we know that these properties, they sort of carry over, right? So we know that.
So basically, what you're saying is that cosmological principle implies two assumptions that we are making about the universe. Which the first is homogeneity. Mm-hmm. So we are saying, okay, zoom the universe out. You are in the universe, you zoom it out, and it's this little piece. And we say the universe is homogeneous. So everywhere I look, it looks pretty much the same. And then the second thing you're saying is, okay, due to the cosmic microwave background radiation, I zoom out, I look around me, and then I go 100 billion, no, not 100 billion, sorry, 50 billion light years in distance, and I say, okay, I assume the universe will look the same also in that point. So basically, you are saying the universe is homogeneous and it is isotropic, meaning it looks the same as looked by any particular angle in the universe, right?
Right, and these two things, they might sound very similar, but they are really they are conceptually different, and this is also gonna tie nicely into this Poincaré conjecture stuff. But like, isotropy of the universe, at least from where we stand, right? Isotropy of the universe is something that we can actually verify, because we just need to, we can look from our perspective in all these different directions. And then if we see the same, we can say legitimately that the universe is isotropic, at least from our perspective, right? But homogeneity, right, which is about these translations over huge distances that light could never possibly have traveled, etc., etc. homogeneity is something that is really, I would say, almost impossible to verify experimentally. Okay, so it's really like, it's really a leap of faith, so to speak, right? And you discussed, for example, in all of these other one of these other podcasts, you have in mind, right, this cosmic web picture, where, you know, with this millennium simulation, right, there's this famous picture with this purple shade, right, where you have these filaments and these lines, etc., etc., and then it's like, okay, this is our understanding of the universe, right? We think
but it's still a simulation.
Yeah, right, but I mean, it's a simulation that we built based on these laws, right? We say that the universe is homogeneous. Okay, well, almost, right? There could be, you know, you discussed this with Jimmy, but right, it's like homogeneous plus some tiny bit, and that tiny little bit can then grow into galaxies and whatever, black holes, the interesting stuff about the universe, right? But when you zoom out far enough, this thing should look the same everywhere. And it's an assumption. It's not something that we can actually, you know, we cannot go take the scientific method and then actually verify that. But it's a crucial underpinning of ΛCDM. And it turns out that, so you combine these two things, right? So symmetries, which is homogeneity and anisotropy, you combine that with general relativity, and then you can get these Friedman equations, and you can start doing all kinds of cool stuff, right? You can calculate things analytically. You can calculate how temperature fluctuations in the CMB, how they ended up forming galaxies, right? Dark matter collapsed into halos, and then baryons came and they formed galaxies, and then black holes, and then came, well, basically everything, right? It's a pretty impressive thing. And that's also why ΛCDM has predictive power, right? Because there are so many symmetries that you don't, like, the model becomes sort of rigid in a sense, that you don't have that much freedom anymore, which means that, right, if you observe things at 5 billion years ago, and then you use this homogeneity principle, right? And you say, okay, now I know about the entire universe at 5 billion years ago. And then that means that I can calculate what is the universe 2 billion years ago. And then I can go look back in my data and I can see, okay, does, you know, at least on my little light cone again, does the universe really look like that? Did the universe really look like that 2 billion years ago? And that's why now all of a sudden, you know, it has predictive power, because you impose all these symmetries. So yeah, that's what I wanted to say about what ΛCDM is like, fundamentally.
Yeah. And how do we have any experimental data that we cannot? Let's say that we are struggling to verify with ΛCDM.
Right. So nowadays, pretty much, I would say a majority of cosmologists think that there are problems with ΛCDM, and probably the most prominent example is, so these are not even the conceptual issues, right? This is not even about, okay, what is dark matter and what is lambda, right? If this model just fit the data perfectly, then okay, we could go worry about what dark matter and dark energy is, but then that would be our main concern. But that's not even, you know, it's kind of worse than that, so to speak, because even this model with all its unexplained features, so to speak, it also doesn't fit the data anymore. And the data that is particularly problematic right now is surrounding this so-called Hubble tension. I don't know if you've heard of this.
No, I am not heard of it.
Okay. So if you go back to the example that I had, where based on homogeneity and isotropy plus these laws of general relativity, you have predictive power, and you have calculations that you can perform that you can then go check against data. And in this case, there are two pieces of data that come from different slices, if you like, different times in the past for which we inferred something, and they don't match. Okay, so what happened was people were measuring the Hubble constant, and the Hubble constant is basically the expansion rate of the universe today. Right, so it's like you have this function that describes how the universe is expanding, and the rate of change of that function is essentially the Hubble parameter. And what you can then do is you can say, okay, I can look. What people do is essentially two things. So they say, okay, I can look all the way back to the time of the cosmic microwave background. I can measure all these temperature fluctuations. I can see how big they are and how well they're spread out, how correlated they are, et cetera, et cetera. And it turns out that allows you to determine what the Hubble constant is today. Because the Hubble constant today, if you look at it the other way around, within this Friedman model, if you know the universe at some specific point in time, then you know what the Hubble rate is at that time, so the expansion rate at that time. And you also know all the other properties, and therefore you can extrapolate that, and you can say, okay, so if that's what it was like back then this must be the expansion rate today. And this you can do using this cosmic microwave background radiation. That's one method. So that's what people in cosmolingo would call the Planck value of H0, because it's this Planck satellite that's measuring these temperature fluctuations. And the other piece of data that we have comes from a completely different time in the universe, right? Because the cosmic microwave background is super long ago, right? It's the universe is now 13, 14 billion years old. But this cosmic microwave background radiation comes from again, also something you discussed with Jimmy, right? When the universe went from being opaque to being transparent, all these photons they started escaping this plasma, right? Mean free path went pretty much to infinity, and that's when the universe was only about 300,000 or 400,000 years old. So that's on that timeline. It's sort of like over here, right? It's very, very far away from today. But then there's another piece of data that we can use to infer what the expansion rate of the universe is today. And that has to do with supernova data, or so-called standard candles. Have you heard of this before? I can briefly explain it.
Yeah, I didn't know they were called standard candles.
Okay. So the idea is, if you imagine that the universe is expanding, and therefore objects are moving away from you at ever increasing speed, or at least that's what we think now, right? Because we think that the universe is expanding in an accelerated manner. But in any case, because the universe is expanding, everything is moving away from us, and the rate at which it moves away from us is related to how far away it is from us. That's kind of that's what Hubble already figured out, more or less, in the 1920s or 30s, right? It's just Hubble's law, and that means that if you have an object which is moving away from you, and you can somehow measure its velocity, then you can also measure its if you know its distance, if you know the distance that it is away from us, then you can also measure its velocity, or the other way around. And what people then
so basically, sorry, just to clarify, actually say it very, very briefly, the Hubble law basically relates the recession velocities of distant galaxies from us, and it is basically implying a direct, proportional relationship between distance and velocity, meaning far further objects in the universe are moving at a greater velocity compared to objects which are relative to us. And this, just for the sake of it, I read it in a very nice book which is called The Big Bang. Just imagine, just to give the picture more clear. Just to, imagine a triangle, 3 points, 1, 2, 3, and if you say, okay, now these 3 points start expanding in direction. In order for these 2 points, you said that we need to have homogeneity, right? And so, since it is our cosmological principle, so due to homogeneity, we want to preserve the shape of this triangle. And in order to preserve the shape of this triangle, we need to keep the angles constant. And how would you do it? Well, you would simply increase the distance between the points proportionally to their current distance between each other, meaning that you cannot increase these, these 2 vertices here disproportionately compared to this distance here, which is greater, because otherwise angles would change, the shape of the triangle would change, and so homogeneity would fade away. That is just a simple interpretation that made me smile.
No, it's true. Okay. It's simple, but it's true. But so the idea is, if we have these supernova, then basically you can imagine, like, if you know what kind of star this is and what the star is made of, right? Because a supernova is basically a dying star. So when a star has exhausted pretty much all of the nuclear fusion that it can employ in its core to keep it from collapsing inwards gravitationally, then it just kind of plummets, and you get this explosion, which is called a supernova. And these supernova events you can observe, and then the idea is, okay, if I know now, if I know sort of the initial flux with the initial intensity, if you like, of this supernova, and I also know the intensity with which I received it, right? Because this intensity is somehow also, it's a measure for distance, right? Because you imagine it's just kind of like an inverse square law, right? This all of this intensity, all of this energy from
the brightness. So the brightness,
yeah, the
is
brightness,
inversely
sure,
proportional to the distance to us. Okay.
Right, right. So that means that if I have lots and lots of data from the supernova, and I know how bright they were intrinsically, just because I know how this star process works, right? I know how this physics within this type of star works, and I know what kind of stuff is ejected, etc., etc. And I also know what came in. Then I can sort of take the difference of the two, and then I can infer the distance. Then I can infer the distance and the velocity of these supernovas to me. Does that make sense?
Yep.
Yeah. So then, because you have that, if you imagine doing that for many, many supernova on the sky, then that also allows you to say something about what the expansion rate of the universe must have been at the times where these supernova exploded, and therefore also what the expansion rate of the universe is today. Yep. So, like by doing that kind of analysis, you can also infer this Hubble parameter H0. So that's so we have the Planck value of H0, and we have the Shoes value of H0. Shoes is what this experiment is called, or these kinds of experiments are called, that take supernova and right from a completely different epoch in the universe, because that's maybe well, also definitely billions of years ago, but not as old as the CMB, right? So it's a different slice that we're trying to look at now. And under all the assumptions of lambda CDM, I should be able to compare the two, and they should match. But apparently they don't. So there's this value of H0 that you infer from Planck, and there's this value of H0 that you determine from the supernova, and they are in tension with one another, right? Both of these experiments, they have like a mean value of H0, and then there is some error, right? But the bell curves for both of them, they don't overlap at all. Like one is just way higher than the other. I think currently it's something like, maybe Planck is 68 plus or minus 0.5, and then the supernova one is 72 plus or minus, 1, let's say.
Okay. So quite many standard deviation away from each other.
Yeah. I think today most people say that it's really gotten to like this 5 sigma level, maybe a little bit less, but yeah, okay, it's a serious problem. And
it is definitely.
Yeah. And well, it could just be still that we don't understand something about either one of these experiments, that we're just calculating something wrong, or we're forgetting about certain physics, or we don't we don't understand it as well as we think we do. But more and more people believe these days that, well, there is actually it's a more serious problem. It's not just systematics. It's really the model that we have is just kind of breaking down.
It's wrong.
Yeah, it's just wrong.
It's not the right one for how beautiful it can be, and that's
exactly.
I think it is quite fascinating, at least to me, understanding, at least grasping the fact that one of the most let's say cutting edge cosmological tool, let's put it this way, that we have developed so far, which describes a huge ton amount of data, is actually already on the bridge of saying we should discard it, we should implement something new. But the point is that we don't at the moment have anything new. So we cannot, or at least anything new that explains more data than lambda CDM. So yeah, that's the thing. And I believe it is. Yeah, I think I just find it beautiful because it gives me the, I'd say, it gives me the insight of how actually much there is to still yet to unravel, to discover. And I think it is quite encouraging for people saying, okay, this is not it. I mean, I think I would have been much more depressed if basically 100% of the observation were described by lambda CDM. Then I mean, cosmologists and physicists would have no job anymore because
no, of course, no. But this is a very exciting time, I think, to do research in cosmology, because they're all, the ground is shaking a little bit, right? And somehow something might happen.
That's great.
But that's great. That's really great. And so just to kind of tie these two things together, right? So this is one problem with lambda CDM, but there are more problems with lambda CDM that I don't really have time to go into, but there is quite a list of them these days. Like Hubble tension is at the top of the list, but there are many other ones which are, well, at maybe a lower level of significance, right? It's maybe like a 3 sigma tension, or could be a fluke, could be nothing, could also be something. And there are also other things for which we say, well, okay, we don't really know what to do with that. It's kind of at the bottom of our list, but nevertheless, it's a little bit weird. We didn't expect that.
Okay.
But the list itself of unexplained experimental facts is quite extensive. And they don't just have to do with H0, they have to do with other parameters of this cosmological model as well, and other assumptions, etc., etc. So then you might say, well, and you actually did kind of say it yourself already. So, like let's say that lambda CDM is not right. Then what can you do? And there are essentially two things that you can do. You can say, well, I'm going to, I will modify, right? I will try to modify my model, lambda CDM. And I will say, well, okay, lambda CDM is like almost correct, but there is some, layer that I need to add on top of some new physics, which explains, for example, this Hubble tension or some other tension that you wish to, define away, so to speak. That's one thing you can do, and this is something that many people have put forward methods by which you can do this. So new physical mechanism, maybe some new particle, maybe some new form of dark energy, maybe axions, maybe primordial black holes, you name it. Many scenarios which can then help alleviate these tensions that keep us up at night. But another thing that you can do is you can go back to like the very bottom of lambda CDM, which is, okay, I'm going to try to touch either general relativity for calculating this evolution, right? I'm gonna modify Einstein's equations, do something else, so that maybe some of these tensions will go away. I will replace Einstein's equations by something else. Maybe there will be another term. Maybe there will be some new field there. And then maybe that will solve my problem. And another thing you can do is you can say, I don't want to touch GR, but I want to touch these symmetry principles. So then what you can say is, okay, I don't really want to assume that my space is homogeneous and isotropic everywhere, but I would rather try to do something that is a little bit more general. So I would like to say, well, what if the universe is not isotropic, for example? What if in the traditional model, so to speak, you had no isotropies. You had no anisotropies pretty much at any point in time, and then they just kind of remained small. But what you can also do is you can say, okay, I'm going to take this Friedman, this FLRW model, but I'm going to replace the geometry of the space-time, so of these space-like slices. I'm going to replace it by something else. And usually, right, in the traditional ΛCDM model, there are essentially three possibilities, because you have this curvature parameter, and the universe can either be flat, open, or closed, and that's basically it. But what you can do is you can say, okay, let's say that my space-like slice in this space-time that I'm trying to evolve, let's say that it's just some three-dimensional manifold which has some kind of which has a translational symmetry, but it doesn't have necessarily this isotropy around every point. And then you're you kind of naturally stumble upon these three-dimensional manifolds and this classification problem that Perelman was trying to attack. And then it turns out that there's actually that there's a list of possible geometries, so to speak, that you can choose from, which are still homogeneous, so still translation invariant. So I retain my predictive power, but maybe there's a little bit of anisotropy that can also evolve over time, which can give me a little bit more freedom, maybe, in describing some of the data that I don't understand.
Okay, and you now mentioned the work of Perelman, but how can, let's say, how can the work that he did for the Poincaré conjecture, how can this work help us understanding the universe, and how does the conjecture per se relates to the general relativity and space-time?
Right. So for that, this was probably not clear right away, and it's also something that I think the details are quite difficult to understand, but the version of the Poincaré conjecture that I explained is the way that the Poincaré conjecture was originally formulated. So it was specifically about this three manifold which has some properties, and then determine whether it's a ball or not. But the work of Perelman, which is about this Ricci flow and the general geometry of three manifolds which might not be balls, is Perelman proved more than just the Poincaré conjecture, so to speak. So, he proved some big thing, which, if you would want to know the technical name, it's called the Thurston geometrization theorem, which, as a particular case or as a consequence of that, also solves the Poincaré conjecture. And what we're really what we're interested in is this Thurston geometrization conjecture, which basically gives like a list of all these possible homogeneous three-dimensional spaces that you can have. How can we apply that to cosmology? And that is of course not the application that Perelman had in mind originally, but that's what we would like to understand. So can we use this knowledge to maybe find some to maybe find some generalizations or alternatives to lambda CDM, so that we actually have alternative models to subject to our data? Because now it's like everything in cosmology has always been about taking lambda CDM and then determining the free parameters that lambda CDM has, because lambda CDM is a super old model in some sense. This model, this cosmological principle, and then combine it with Einstein's equations, it goes all the way back to the 1920s, when people really didn't have data at all. And now finally we have data, and we can test this lambda CDM model very, very precisely. And that has worked for some period of time, but as our data gets better and better, and these error bars, they keep shrinking and shrinking and shrinking, and at some point the model will start to give, and that's kind of where we're heading right now. So we need to, I think, we need to focus on having viable alternatives to lambda CDM. Which are not just about taking lambda CDM and then adding more layers of complexity on top, but also really understanding, okay, how can I take these fundamental assumptions of lambda CDM, and which ones of those can I discard or maybe keep, and then in order to do that, well, it's quite difficult, because if you have a model with a very large number of symmetries, like this traditional lambda CDM model, then computing things analytically and really understanding at a very detailed level how everything works and how everything evolves from the far past up to now is possible, because the model is simple enough to do that, so to speak. But then if we try to let go of some of that simplicity, then we're going to have to work pretty hard to actually predict something that we can understand.
Okay, clear. And yeah, do we have any, let's put it this way, do we have any potential concrete and current application for the Poincaré conjecture in cosmology? And does the work of Perelman helps us? Actually, how can the work of Perelman help us construct new cosmological models?
Right. the work of Perelman, in a sense, what he proved, you know, we could have also done this without the work of Perelman, because, you know, this conjecture already existed, right? So we could have just said, okay, we're going to assume that this conjecture is true, and then we have certain options for these geometries of these manifolds that we can choose from, and then that's it. But now, you know, we can be very sure that this is really the entire list, so to speak. So that's, in that sense, it's kind of reassuring, if you like. Sorry, let me just put on my lamp. But right, so with this work of Perelman and this conjecture by Thurston, which is now proven, we have a list of geometries that we can pick and say, okay, what if we what if we replace lambda CDM by this three-dimensional model? And then there are things that you can calculate still within these more complicated models. Maybe not everything right away because it's more complicated, but some things we already know how to calculate within these more complicated models. And these are, for example, let me see. So one thing that you could calculate is when you consider radiation from the cosmic microwave background in this more general spacetime, and when it travels towards us, then if this geometry is a little bit more complicated, then these bundles of light, they can sort of get twisted as they travel through space, you know, from this CMB surface to us. And if we could, for example, see such a twisting, or if there is another effect which is related to whether, for example, the universe looks the same as its mirror image or not, which is also an assumption that is made in this in all of these traditional lambda CDM models. For these more general geometries, that doesn't have to be the case, which would mean that if you find such a signal in this cosmic microwave background radiation, then some alternative model like that could help maybe explain it. But yeah, this is all you know. I'm also not sure yet, right? This is something that we're not entirely sure about, but we do know that people have tried it in the past, like using some of these alternative cosmological models and calculating something, and then seeing if it was supported by the data. And most of the times it didn't really yield anything interesting, mostly because, well, the quality of the data was maybe not as good as what we have now. But if we were to redo these tests today, then maybe some interesting things could happen. And presumably also, if we manage to if we manage to increase our understanding of what the universe looks like within these models. So also, for example, how dark matter will evolve and how these halos and galaxies will form, etc., etc. Then we could also try there if there's really some observational difference between the ΛCDM model and one of our more complicated Perelman models, so to speak.
Okay. So do you believe that, let's say, that maybe at the end of the day, one of the great insights that can lead us to a new cosmological theory can ultimately be derived from the pure and hardcore geometry of, let's say, the space that we are embedded in? Or do you think, sure enough, it will be, let's say, the field, the subject that this further insight will derive from, it will clearly span many topics, many subjects. But do you think that geometry, because from what you're saying, it sounds like, and I personally also, if I have to express an opinion, and I say, well, look at how much Einstein, let's say, revolutionized our understanding of the universe. And basically, if you want to put it very brutally and also, let's say, very approximately, his work was basically about geometry, like about the geometry of space-time. Okay,
yeah,
how these curves, how these behave, but it is like the geometry that we are embedded in. And so, do you think that, let's say, further insight clearly may derive from data, instruments, new observation, or whatever it is, but do you believe that at the end of the day, the main fundamental insight will be from, let's say, some pure geometrical aspects?
I think if that turned out to be the case, then I mean, I've been in theoretical physics and math for a pretty long time, and I've seen a lot of weird and beautiful things. So at some point you get used to this. But if that were true, that we live in one of these exotic geometries, and somebody can irrefutably come up with some experiment, like like when something like when people found the Higgs particle, right? There was like it was like this huge discovery, and then nobody could come around it. If that turned out to be true, then I would really marvel at that. That would be something that it would definitely blow my mind. And I would also say that I think, despite the fact that general relativity is very old, comparatively old, let's say, it was formulated well before we could do cosmology as an actual science. But in my personal opinion, general relativity and synonymously geometry is just it's a really, really difficult thing to understand. Like this Einstein equation, it's just one line. How bad can it be? I think it's enormously complicated. Like you can make lots of simplifying assumptions, and then you can get some approximate picture, which is ΛCDM. But even solving Einstein's equations in less simplified setting and really understanding everything that's going on, and how is this light propagating, how is this matter evolving, blah blah blah. It's extremely complicated. It's not like oh, GR is 100 years old, we understand GR. I think GR is hugely complicated, and today the way that it's applied in cosmology, it's not really complicated because all these simplifying assumptions are made, and then you can understand intuitively quite well what's going on. But this full theory without any symmetry assumptions and all of the subtleties that go with that is hugely complicated. So that's really unexplored territory, in my opinion, or at least as far as I know, which makes me, which makes me think that, before we, if it turns out that these problems with ΛCDM persist, then the natural place to look, I would say, is to not modify GR, like try to change that, but first, really make an effort to understand what this geometry is all about, and how it works in more complicated settings, because this is something that I think this is a huge task in and of itself. It's a really, really complicated theory, general relativity. And so I think, I would not be, given how rich it is, given how rich general relativity is, I would certainly not be surprised that somewhere in that zoo is something that describes actually what the universe is, really, as a geometrical object.
Mm-hmm.
But I mean, that's also my hope, I guess, because it would be super pretty, right? You would still have only this one equation, and then maybe some other more real world stuff, but then that would be enough. And I think that would be pretty poetic if it's true.
Well, we hope it is, but we cannot say it at the moment. But
I think sadly not, right? But that's what keeps us going.
Exactly. It's precisely where I think many people and I mean the proper scientists and also the non let's say only the enthusiasts, so people without formal education, who just do this for the sake of fun. I think it is very stimulating, the fact that there are many open questions that are still so much intrinsic, so much fundamental, and the fact that with quantum mechanics and general relativity, a huge amount of data have been explained, they have been tested up to incredible amount of precision, but still we can grasp that there are very intrinsic question about where we live that we cannot even barely, let's say, touch. We cannot even give a rough answer. We just have to how you say, raise up our shoulder and say, well, we don't know how that is. So I think that is very fascinating, and hopefully it will be reason maybe for another visit, another podcast that we may have in the future, if we have any further responses from physics and cosmology into the mysteries, into what are the mysteries of the universe. So I think we can wrap it up here. It was very interesting. I really liked very much because the Poincaré conjecture. I've been let's say watching some the classical videos of number file. those standard YouTube channel covering this topic, which they give a quite, let's say, nice introduction to it. But then I think it is also fascinating as pretty much everything to relate it to something else, which is at the same time fascinating, and in our case was cosmology. So that is also, when you told me about the topic, I was quite surprised. I was, well, this appeared to be having no relation at all, but
no,
ultimately
but
they do.
yeah,
So,
there is. It's yeah, it's where pretty math and nice physics come together, right? That's a good place to be, I think. I only heard about it very recently as well, and in some sense it had been around for quite some time, but then when this Perelman conjecture, or when this Poincaré conjecture was eventually solved, it now really gives us like a sort of a unified understanding of what these things are, and how they might have something to do with reality. So yeah, I'm very eager to see if maybe me myself during my PhD I will do some research on this, and if not, then I'll definitely keep learning about it myself, because I think this is a very interesting avenue. Yeah.
Okay. Yes. Hopefully we can have indeed another episode on further developments. Yeah, maybe you can come back again and tell us about some finding you have made on where you can connect Perelman work with geometries or space-time. So
I mean, we'll certainly. I'll keep it in mind. If any revelations happen, then
keep us posted.
You will know. Yeah.
That's great. Okay.
Okay.
So, yep. I think we can close it here. So.
Okay. Yeah. Thanks for having me.
Thanks.
It was great.
No, thank you, Thomas, for your time, for your explanation. It was really a pleasure to me, and also thanks to everyone who is listening on this Tuesday night. Maybe the episode will go online a bit later, but yeah. So thanks everyone for being with us, and yeah, I will see you in the next episode.
Okay.